So a very good afternoon everyone. Welcome back to the fundamental course for strength of material. In the previous two sessions, we have already discussed about few of the basics, how loading are applied over any member, and once the loading is applied, how the internal resistance is developed. And this internal resistance developed per unit area is termed as stress. Okay. Now we will going to see what is the basic relation between stress and strain. So this relation of stress and strain was given by a scientist named Hooke's. He gives the Hooke's law which defines the relation between stress and strain. Before that, Hooke's has assumed these three assumptions before giving his law. The first assumption was material is homogeneous. I have already told you that if the material is homogeneous, it means it has the same property in any one direction, right, or in all the direction. Then for suppose you are moving in x direction, so the property of the material will remain same. Similarly, when you are moving in y direction, the property of the material will remain same. Similarly, when you are moving in the z direction, again the property of the material will remain same. The second assumption is material is isotropic. It means that at a particular point in all the directions, the property of the material will be same. So when you combine these two and you say material is homogeneous and isotropic, it means no matter at what point you are present inside the volume of the material, the property of the material will be same. Okay. The third assumption is material is elastic. And what do we mean by elastic material? Elastic material is that material which will going to regain its original shape and size once we remove the load. So these three assumptions Hooke's has assumed while giving his law. Hooke's has given a relation between stress and strain. Now looking into what do we mean by Hooke's law, right? So for suppose this is the case for axial loading. You have an axial loading like this. This is the case for axial loading. For this axial loading, load is acting like this. This is my load P, right? Due to this axial load, there will be some internal resisting forces that are developed. So this is the internal resisting force. Due to this internal resisting force, internal stress will develop inside this material, right? And also due to this load, there will be some elongation happening to the bar. So the deformed shape of the bar will look like this. This is my deformed shape of the bar. This is the deformed shape of the bar. This is my deformed shape of the bar. So earlier the length was L0. This length was L0. And now the length has increased to L dash. So this change in length that happened, delta L, is equal to L dash minus L0. Okay. And when we talk about strain, so strain is nothing but change in length divided by the original length. In our entire analysis of strength of material, we will be using engineering stress only. We will not be using actual stress. So this is your engineering strain that is calculated. Similarly, your engineering stress sigma is equals to the internal resisting force divided by per unit original area. So this is my again engineering stress. So no matter we are using strain or stress, both will be engineering stress or engineering strain because we are using original length and original area, right? This resisting force per unit area is equal to this external load applied P. So this stress can be written as P by A naught. P by A naught, okay? Between these two, strain and stress, Hooke's has given one relation. And Hooke's says that your stress is directly proportional to strain. And even if you use common sense says that if a body is getting more and more deformed, okay, if you are deforming this body like anything, this body will produce more amount of internal resistance. The amount of deformation that body undergoes similarly is proportional to the amount of internal resistance developed in the body. So what Hooke's law says? Hooke's law says that your stress is directly proportional to strain. Your stress is directly proportional to strain. And removing this proportionality sign, you have stress is equals to E into strain. And this is my Hooke's law for axial loading. So this is my Hooke's law for axial loading, right? Your stress is directly proportional to strain, and removing this proportionality sign, this constant comes, and this constant is known as the Young's modulus. This E is termed as the Young's modulus. This E is termed as the Young's modulus. Okay. Now the question arises, sir, out of stress and strain, which one is causing the other one? Question is whether due to this stress, strain is produced, or due to this strain, stress is produced. So the question is very simple. Out of stress and strain, which one is a dependent variable? Which one is a dependent variable? So what is my question? Question is, tell me whether stress is dependent on strain. Stress is dependent on strain, or strain is dependent on stress. Strain is dependent on stress. You have to analyze this. If you analyze this, you will come to one point that once you apply load over any body, that body undergoes deformation. Okay. So first, strain will come. When you apply load over any body, this body will undergo deformation and strain will come to this body. In order to resist this strain, in order to resist this deformation, internal resisting stresses are produced, internal resisting forces are produced. So first, the body undergoes deformation. Due to this deformation, strain will come, and in order to resist this strain, internal resisting force will develop in the body. And due to this internal resisting force, your stress will develop in the body. So this statement is true. Your stress will be dependent on strain. So this statement is true. Your stress will be dependent on strain, and this one is false. What I am saying, if this is my body, and I apply external load over this body, due to this external load, this body will undergo some deformation. Like this, right? This body will undergo some deformation. In order to resist this deformation, in order to resist this deformation delta, in order to resist this deformation delta, in order to resist this deformation delta, this body will produce internal resisting force. And this internal resisting force is termed, per unit area, is termed as stress. So your stress will be the function of strain. Your stress will be the function of strain. So this is your strain will be your independent variable. And stress will be your dependent variable. That's why every time when you see the stress strain plot, you will see that strain is always drawn on the x-axis An x-axis or the horizontal axis is an axis of independent variable. So your stress is dependent on strain. So every time you have a function like this, your stress will be a function of strain. So I hope this is very much clear to you. So this is the Hooke's law for the case of axial loading. When you apply the axial load, this axial load will produce deformation, which will produce strain. And in order to resist this strain, internal resisting force will be there, and this internal resisting force per unit area is termed as stress. So according to Hooke's law, your stress will be proportional to strain. If you look into this Hooke's law, your stress is equal to E into strain. This stress is P by A and strain is delta L by L, right? If you just substitute the value, you will get P by A is equals to E times of delta L by L. Just take everything this side. So your deformation delta L is equal to PL by AE. So this is your deformation that is happening to the bar, and this deformation is equals to PL by AE. Using this relation, you can directly calculate this deformation. Now here I would like to add one point. This A is the area of cross section of the bar and E is the Young's modulus. Okay, A is the area of cross section of the bar and E is the Young's modulus. This AE combinedly known as, this A and E is combinedly known as axial rigidity. Now I'll give you one very beautiful concept how to analyze any bar using this term, axial rigidity. Okay, just imagine you have two rods. One is made up of steel and another one is made up of plastic. So this is my steel rod and I have another rod which is made up of plastic. These two are two rods, right? This is steel and this one is plastic. Okay. If you apply the same load over both the bars, same P load over both the bars, right? Oh, same P load over both the bars, and cross-sectional area for both the bars is also same. Cross-sectional area for both the bars is also same, right? A and A is the cross-sectional area which is same for both the bars. I think it is very easy to understand that when you apply same load on both the bars, plastic bar will be easy to get deformed, right? Whereas for steel bar, more amount of internal resisting force will be there against the deformation. Okay. Now why I am telling you this? You can also analyze that for this steel bar, your axial rigidity will be more, right? Axial rigidity is nothing but how much resistance a particular member is offering against the horizontal or axial loading. Axial rigidity tells us about how much internal resistance will be developed in a structure against the axial loading. Okay. So if AE is the axial rigidity, AE will going to tell us about the internal resistance developed in the structure against the axial loading. So this AE tells us about, this AE tells us about this AE tells us about, so axial rigidity AE tells us about tells tells us about amount of internal resistance, amount of internal resistance against axial loading or against axial deformation, because axial loading will cause axial deformation, so one of the same thing. So if any statement comes in your GATE exam or any technical exam where you need to compare members depending on their axial rigidity, so you will clearly identify that whichever member has more value of axial rigidity, it will be more difficult to deform such members, right? So if you look into the example of steel bar and plastic bar, axial rigidity AE for a steel bar will be more than that of plastic bar. That's why steel bar will be more difficult to deform than your plastic bar. So I'll write this: axial rigidity of steel, this is axial rigidity of steel, will be more than axial rigidity of plastic, right? Since both the areas are same, we clearly know that Young's modulus for steel is more than Young's modulus for plastic, right? So this is how we define the deformation using axial rigidity. Axial rigidity will simply going to tell us how difficult it is to deform any bar. If a bar has more axial rigidity, it is more difficult to deform, okay? Again, for this expression, there is one term which is known as AE by L. AE by L. And this AE by L is known as axial stiffness. This AE by L is known as axial stiffness. So again, axial rigidity will be for the whole length of the bar. So this amount of difficulty you will be facing to deform unit length of the bar is termed as your axial stiffness. So how much difficult it is there to deform a unit length of the bar is termed as your axial stiffness. So I hope this is very much clear to you. So if any statement comes in the examination that two bars are given, their axial rigidity are given, and you need to compare which bar is more strong. So you will say, sir, whichever bar has more axial rigidity will be more strong. Okay, directly you can say this. So this is all about your first law, which is known as the Hooke's law for axial rigidity. Okay, chalo. Now moving on to our next topic. And next topic we will going to discuss about Young's modulus. What is Young's modulus? Okay. So while drawing the stress strain curve, you might have observed for mild steel. So if this is my stress strain curve for mild steel, okay. So this is my stress strain curve. This is my stress strain curve for mild steel. Okay. So the initially your stress is proportional to the strain, and this part of the curve is linear. This part of the curve is linear, and A is known as the proportionality limit. The slope of this line, the slope of this linear part of the curve is known as your Young's modulus E. So the slope of OA, slope of OA is Young's modulus. is Young's modulus. So slope of OA is Young's modulus. And this OA is linear. This OA is linear. This OA will be linear. This OA is linear. Right? But A is the point till which your Hooke's law is valid. Beyond point A, there will be some non-linear part of the curve and it is still under the elastic limit. So this will be your non-linear part of the curve. This is your non-linear part of the curve. This OB is your non-linear part of the curve. This AB, sorry, not OB, AB is the non-linear part of the curve. Non-linear part of the curve is AB. And B is my elastic limit. So B is elastic limit. So Young's modulus is for only slope of OA. The slope of this non-linear part AB is termed as the tangent modulus. The slope of this non-linear part AB is termed as the tangent modulus. This slope is termed as the tangent modulus, right? So the slope of this non-linear part AB is termed as the tangent modulus. Slope of non-linear part AB is called tangent modulus. The slope of non-linear part AB is termed as your tangent modulus. Okay. So there are two modulus. First one is the Young's modulus, which is the slope of this linear part AB OA. Sorry. Then slope of this non-linear part AB is termed as the tangent modulus. Now there is one more modulus that is known as the secant modulus. Now understand this very carefully. What do we mean by secant modulus? Okay. So for secant modulus, if you take any point on this non-linear part AB, for suppose you took this point, right? You took this point on this non-linear part AB. And if you join this point with the origin, right? So this is the line joining this point with the origin. So this is my some point E, and I have joined this point with the origin. Okay, not take E because you will get confused. Say this point is some point G. This point is G, right? The slope of this line joining the point on the non-linear part with the origin, this slope is termed as your secant modulus. This slope is termed as your secant modulus. Right? So if you look into the linear part, your Young's modulus and secant modulus will be same because this is a straight line. But when you look into the part AB, your secant modulus and tangent modulus will be different. So what is a secant modulus? Secant modulus is the slope of the line joining the point on the non-linear part with the origin. And this is termed as the secant modulus. So slope of line joining the point on stress strain curve till elastic limit with origin is called secant modulus. So in the linear part AB, your secant modulus and Young's modulus will be same. And but in the non-linear part AB, your secant modulus and tangent modulus will be different. So I'll just write this down. I think this one is hidden. Slope of line joining the point on stress strain curve till elastic limit with origin is termed as secant modulus. Next point is for linear part AB, for linear part OA, not AB. For linear part OA, your Young's modulus will be equal to secant modulus. And for non-linear part AB, for non-linear part AB, tangent modulus and secant modulus will be different. Is not equal to the secant modulus. So these are the three varieties of moduluses that we have. For Young's modulus, it is very much simple. Young's modulus is the slope of the initial part of the stress strain curve, and that is the linear part. Till point A, up to which the Hooke's law is valid, that part is known as, the slope of that part is known as the Young's modulus. Okay, so I hope you have understood all the three varieties of moduluses that we have: Young's modulus, tangent modulus, and the secant modulus. The slope of OA is Young's modulus, the slope of non-linear AB is the tangent modulus, and the slope of the line joining the point up to the elastic limit with the origin, the slope of this line is termed as the secant modulus. So I hope this is clear to you. Okay. Chalo, moving on with this. Next topic of discussion is the Hooke's law for shear loading, right? In the previous class, we have discussed how we get the shear stress and how we get the shear strain. So, just consider this example. if you have a material like this, if you have a body which is resting like this over the surface, okay. So this is one body which is resting over the surface. If you apply one tangential force over its surface, if you apply a tangential force like this over its surface, if you apply the tangential force over its surface like this, so this is the tangential force that you have applied over this surface. Due to this tangential force, this body will undergo deformation in this fashion. This body undergoes deformation in this fashion. So this is the deformed shape of the body. This is the deformed shape of the body. So this is my deformed shape of the body. Right? And this deformation is measured by this angle. This angle is known as your shear strain. This angle is known as your shear strain, right? So shear stress tau is shear force divided by area, and shear strain phi is equal to your delta L by H. This is your shear strain, delta L by H. Now Hooks has given the relation between these two also, shear stress and shear strain. Hooks simply says that your shear stress is directly proportional to your shear strain. And again, your shear stress will be the dependent variable and shear strain will be your independent variable. Okay. Due to the shear strain, in order to resist the shear strain, your shear stresses will be developed in the body. So when you remove this proportionality sign, you have tau is equals to G into phi, and G is known as modulus of rigidity. G is known as modulus of rigidity. Modulus of rigidity, and this is also known as shear modulus. It is also known as shear modulus. This is also known as shear modulus, right? So this is the simple relation where the Hooke's law is defined for shear stress and shear strain. Again, your shear stress will be the dependent variable and shear stress will be depending on your shear strain, okay? So this is the Hooke's law for shear loading, okay? Moving on with this. Next, we have the Hooke's law for hydrostatic loading. What do we mean by hydrostatic loading? For suppose you have one ball, okay, and you have this steel ball and you have just poured it into the water. So when you pour this ball inside the water, for suppose this is the tank full of water, and in this tank you have just filled or you have just poured the steel ball or say any ball. So this is the ball that is inside. That is inside the water, right? This is the ball which is inside the water. This entire thing is filled up of water or any fluid. This entire thing is filled up of any fluid, okay? What you will observe is for this wall which is inside this fluid, over this wall, along all the three directions x, y and z, same amount of load will be there. For this type of ball which is inside any fluid, along all the three directions, same amount of load will be there. Due to which it doesn't matter whether it is x-axis, y-axis or z-axis, same amount of load will be there. So along x-axis, say sigma is acting. Along y-axis, again say sigma is acting, and along z-axis, again sigma is acting, right? Similarly, along all the axes, same amount of load will be there. So this is your sigma, this is also your sigma, and this is also your sigma, right? So along all the three axes, your same amount of load will be acting over this ball, right? So the change in pressure delta P is same. Your change in pressure delta P is same along all the axes. Along all the axis. Due to this change in pressure, that is of the nature of compressive, right, which is of compressive nature. Due to these compressive stresses that are acting over the ball, this ball will undergo some change in volume, okay. So due to this compressive pressure, you will see the change in volume of this ball. So say change in volume is equal to delta V, and original volume is V. Original volume is V. So this ratio of delta V by V is termed as your volumetric strain. So this ratio of change in volume to the original volume is termed as volumetric strain. So volumetric strain is epsilon V, which is nothing but delta V by V, right? What happened is, over this ball, compressive loads will be applied, and same amount of compressive loads will be applied in all the three axes or along all the three axes. Due to this compressive load, this ball will undergo some change in volume. This change in volume is denoted by delta V, and the original volume of the ball is V. So the ratio of delta V by V is termed as your volumetric strain. So again the Hooke's has given the law between your change in pressure and your volumetric strain, okay. So according to Hooke's law, your change in pressure minus, because it is of compressive type, so minus delta P is equals to, or minus delta P is directly proportional to your volumetric strain, and it is as simple as that to understand. More the amount of pressure you will apply, more will be the change in volume you will observe, and more will be the volumetric strain, okay. So your change in pressure is directly proportional to your volumetric strain. Your change in pressure delta P is equal to K into volumetric strain. So this is the Hooke's law for hydrostatic loading, and K is known as the bulk modulus. K is known as the bulk modulus. I'm writing here, K is the bulk modulus. K is termed as the bulk modulus. So you can write your change in pressure is equals to K into volumetric strain. K is your bulk modulus, and if more is the value of bulk modulus, it means the body will show more resistance against the deformation, right? It will be more difficult to deform the body if the value of bulk modulus is more. So if K is more, then it is difficult to deform the body. Also, you can see from this relation, your K is equal to your minus change in pressure divided by your volumetric strain. So if K will be more, it will be more difficult to deform the body, hence your volumetric strain will be less. So if K is more, if K is more, then your volume change will be less. Hence, your volumetric strain will also be less. So if you have more value of bulk modulus, it means that it is very difficult to deform the body. And we can directly say about a body कि if your bulk modulus is more, then your volumetric strain will be less, your change in volume will be less. So if change in volume will be less, it means your compressibility will be less. And what is compressibility? As the word says, compressibility means how easy it is to change the volume of any body. Okay. So if your bulk modulus is more, your volume change will be less. And if volume change is less, it means your compressibility will also be less. So what it tells us that your bulk modulus K is also inversely proportional to your compressibility. Bulk modulus is inversely proportional to your compressibility. More will be the bulk modulus, less will be the compressibility. Less is the bulk modulus, more will be the compressibility. So you can keep a check on this relation also. So what is the relation between bulk modulus and compressibility? They are inversely related. And if I talk about inversely related, it means that if the body has more bulk modulus, it will going to have less compressibility. Okay. So this is how all the three things are related. We have seen Hooke's law for axial loading, Hooke's law for shear loading, and Hooke's law for your hydrostatic loading. So if I just write down all the three Hooke's law for axial loading, I'll say stress is proportional to strain, or stress is equals to E into strain. Then for shear loading, you have your shear stress is equals to modulus of rigidity into your shear strain. Then for hydrostatic loading, you have change in pressure minus delta P is equals to K into your volumetric strain. Okay. So these are the three Hooke's law, and we have seen three elastic constants. This E, G and K are termed as elastic constants. So this E, which is the Young's modulus, E, which is Young's modulus, G, shear modulus, or modulus of rigidity, K, bulk modulus, are termed as elastic constants. One more elastic constant is there. One more elastic constant is there. Which is termed as the Poisson's ratio. Which is termed as the Poisson's ratio. Right? So basically, we have four elastic constants. Three of them are written here. We need to discuss one more, which is the Poisson's ratio. Okay. Moving on with this. So first of all, just solve this question. you have one very simple question in front of you, which says that a metal sphere of volume 7500 mm cube is subjected to the all-round fluid pressure of 200 megapascal, right? The bulk modulus of the material is this much, the volumetric change is. So you need to calculate the change in volume for this, right? So you have a metal sphere. So let me draw this metal sphere quickly. So this is my metal sphere. For this metal sphere, volume of this metal sphere is 7500 mm cube. So I'm just writing all the data which is given to me. So volume is 7500 mm cube. Volume is 7500 mm cube. And it is subjected to the all-round fluid pressure of 200 megapascal. It is subjected to all-round fluid pressure of 200 megapascal. So this is my all-round fluid pressure. This all-round fluid pressure is 200 megapascal. So this minus delta P is 200 megapascal. So this is 200 megapascal. Next, bulk modulus of the material is given as, so value of K is given to us. K is 1 into 10 raised power 5 Newton per mm square. And in the last class, I have already told you that this Newton per mm square is nothing but the megapascal, okay, MPa. This Newton per mm square is MPa. Now we need to calculate the change in volume. So for calculating the change in volume, if I have the volumetric strain, then it becomes very easy. So what I will do, as per Hooke's law, your minus delta P is equals to K into epsilon V, right? Minus delta P is 200 megapascal. This is 200 megapascal. I am writing all the units. Bulk modulus is 1 into 10 raised power 5 megapascal. 1 into 10 raised power 5. This is megapascal. And then I have the volumetric strain. And volumetric strain is delta V by V. So this is the volumetric strain, okay. So this minus 200, so this is minus 200 megapascal into 1 into 10 raised to power 5. This volume is given to us as 7500 mm cube. This V is given to us as 7500 mm cube. So I'll write minus 200 is equals to 10 raised to power 5 into delta V upon 7500. Just quickly do the calculation and calculate the change in volume. The negative change in volume means that this volume will be compression. This volume will be reduced. Negative change in volume means the volume will be reduced. Just do this calculation quickly. So this is like 200 into 7500 divided by, okay. So this comes out to be like 15 mm. So delta V comes out to be minus 15 mm. This delta V comes out to be minus 15 mm. This delta V is minus 15 mm. So I hope this is clear to you. This delta V is minus 15 mm, okay. So this is how you need to solve this question. Next is your lateral strain and the Poisson's ratio. So we have already seen one type of strain, okay. So before moving to that, you need to understand what are the different types of axes that are present. So if you look into this body, this is my body. If you look into this body, right? I have applied one load like this. So this is my load P that I have applied over this body. This is the load P that I have applied over this body. Due to this load P, there will be deformation in this bar. There will be deformation in the bar, okay? There will be some deformation in this bar. But understand this. This axis which is along the length, the axis which is along the length of the bar, this axis is termed as longitudinal axis. This axis which is along the length is termed as longitudinal axis, which is along length. The axis which is along the length is termed as the longitudinal axis, or the axis corresponding to the largest dimension is termed as the longitudinal axis. So this is my longitudinal axis which is corresponding to the largest dimension for this body. Okay, so this is my one axis. Perpendicular to this axis, I will be having two axes like this. This is my one perpendicular axis. This is my one perpendicular axis. For suppose this is the face of the material, this is this face. For this face of the material, the axis which is going perpendicular to this plane is termed as the longitudinal axis. The axis which is parallel to this plane, this is my first transverse axis. This is my first transverse axis, or known as lateral axis. This is my first transverse. This is my first transverse axis. This is my first transverse axis which is perpendicular to the cross section. The another transverse axis will be like this. This is my another transverse axis. This is my another transverse axis which is again perpendicular, parallel to the cross section. If you look into this cross section, this is my one transverse axis, then this is my another transverse axis. So corresponding to this longitudinal axis, I have two transverse axes. I have two transverse axes. This is my another transverse axis. And what are transverse axes? Transverse axes are parallel to cross section. Transverse axes are parallel to cross section. Okay. The strain corresponding to longitudinal axis is termed as longitudinal strain. So the strain corresponding to longitudinal axis is longitudinal strain. Is longitudinal strain denoted by epsilon L. So epsilon L is nothing but the longitudinal strain. Okay. When you observe this body, again I'll draw this diagram. If you have Okay. If I apply one axial load over this body like this, due to this axial load, this length of the member will going to increase, but this width or height of the member will going to reduce. This height of the member and width of the member will going to reduce. So if you look into the new picture, this new picture looks like this. This is the new picture where height is also reduced and the thickness is also reduced, right? So this is my new width B dash. This is new height. This is new height H dash, and this length is L dash, new length, right? Earlier the width was B, height was H, and length was L, right? So L is increased to L dash. So we write change in length is equal to delta L, which is nothing but L dash minus L. But due to this tensile load, your other two dimensions are reducing. So B and H is decreased to B dash and H dash. To B dash and H dash. These two dimensions are decreased to B dash and H dash, right? So we can also write the change in width and the change in height. So the change in width or change in height corresponding to this loading is termed as the lateral strain. So what is lateral strain? Lateral strain is change in width per unit width or change in height per unit height will be your lateral strain. So lateral strain is your change in width to the original width, or it is equal to the change in height to the original height. And your lateral strain will always happen about transverse axis. Your lateral strain will always be perpendicular to the axis whatever you are analyzing, right? You can write down transverse axis, no problem. It is transverse axis, right? So one relation is there which defines the relation between lateral strain and the longitudinal strain. So the relation between lateral strain and longitudinal strain is defined by a parameter which is known as the Poisson's ratio. So Poisson's ratio is denoted by mu. It is nothing but minus of lateral strain to longitudinal strain. So this is your Poisson's ratio, right? Just have a break for 2 minutes and we will then so we are discussing about the Poisson's ratio. Poisson's ratio is simply minus times of lateral strain to the longitudinal strain. So this is how we have defined the Poisson's ratio. This minus sign is because when you apply the tensile load, your other two dimensions will going to compress, their dimensions will going to reduce, right? So in order to account for reduction of this dimension, we have provided the minus sign for writing the Poisson's ratio. So Poisson's ratio is minus lateral strain to the longitudinal strain. So every time if longitudinal strain is tensile, if longitudinal strain is like it is expanding, your transverse strain or your lateral strain will be like getting reduced. Okay, so always they are of opposite nature. So this is how you define the Poisson's ratio, and Poisson's ratio is the fourth elastic constant that we have. Now next we will going to see what is the relation between all these four elastic constants. What are four elastic constants? First one is your Young's modulus E, second one is your bulk modulus K, then your shear modulus G and your Poisson's ratio. These are the four elastic constants that we have. Okay, so the basic relation that exists between these elastic constants. So first relation is E is equals to 3K into 1 minus 2 mu. E is equals to 3K into 1 minus 2 mu. This is the first relation. This is my first relation. Now observe this very carefully, this relation. If body is incompressible, if body is incompressible, if body is incompressible or rigid, if body is incompressible or rigid, right? For such type of bodies, your change in volume is zero. For incompressible bodies, change in volume is zero. Change in volume, delta V is zero. If change in volume is zero, it means that your volumetric strain epsilon V will also be equal to zero. So change in volume is zero, so your volumetric strain is also zero. We know this, K is equals to minus delta P by epsilon V, that is the volumetric strain is zero. If volumetric strain is zero, then the value of K will be like infinity, will be like very high, will be like approaching to infinity. So if epsilon V is zero, if epsilon V is zero, it means K is approaching infinity, that is very high, right? K is approaching infinity. Just consider the incompressible body. For an incompressible body, the value of K is approaching infinity. For incompressible body, K is approaching infinity. Use this relation here. So you will have E is equals to 3K into 1 minus 2 mu. You take K this side, so this term will become 0. E by 3K will be equal to 0. So this E by 3K, this will be equal to 0 because K is approaching infinity. So E by 3K will be 0. It means that which is equal to 1 minus 2 mu. Okay. So directly we can say from here that your mu is equal to 0.5, your mu is equal to 0.5 for incompressible bodies. So if in the question it is given that a body is an incompressible body, be clear in your mind, for such bodies your Poisson's ratio will be 0.5 always. So mu is 0.5 for incompressible or rigid bodies. Mu is 0.5 for incompressible or rigid bodies. Please keep a check on this. So this is the first relation between elastic constants, where E is equals to 3K into 1 minus 2 mu. And from here we have seen that for incompressible or rigid body, the value of Poisson's ratio is 0.5. Okay. Moving on to the next relation. Second is E is equals to 2G E is equals to 2G into 1 plus mu. E is equals to 2G into 1 plus mu. This is the second relation. So third relation is E is equals to 9 kg by 3k plus g. And last one, mu is equals to 3k minus 2g upon 6k plus 2g. So this is the relation that we have, and these are the relation for elastic constants, right? So E is equals to 2g 1 plus mu. Next is E is equals to 9 kg upon 3k plus g, and last one, mu is equals to 3k minus 2g upon 6k plus 2g. So these are the four different relations between elastic constants that we have. Okay. Chalo, moving on with this, we have one question which says that a circular bar of diameter 50 mm. So I'll write this solution. Circular bar. So diameter is given as 50 mm. To pull of 50 kilonewton, the elongation length was recorded to be 0.09. So the pull load is given as 50 kilonewton and elongation delta L, this is delta L, 0.09 mm. Next, the reduction in diameter is 0.006 mm. Delta D is given as 0.006 mm. Delta D is given as 0.006 mm. Calculate the Poisson's ratio and the value of 3 moduli. Take the length as 250 mm. Length you have to take as 250 mm. So first of all, your longitudinal strain is equal to delta L by L. So delta L is given as 0.09, and L is given as 250. So this is my longitudinal strain. Next is lateral strain. And lateral strain is nothing but change in diameter delta D to the original diameter D, delta D by D. So delta D is given to us as minus 0.006. This is the reduction in diameter, minus 0.006, and the original diameter is given as 50 mm. So this is your lateral strain and this is your longitudinal strain. So for calculating the Poisson's ratio, it is very simple. Poisson's ratio is lateral strain to longitudinal strain with a minus sign. So your Poisson's ratio mu is lateral strain with minus sign to the longitudinal strain. So lateral strain is given as 0.006 by 50, and minus will going to cancel out each other. So this is 0.006 divided by 50. And your longitudinal strain is 0.09 divided by 250. This is 0.09 divided by 250. So you can calculate this to get the value of Poisson's ratio. So this is 1 times, this is 5 times. So 5 you take into the numerator. So this will be like mu is equals to 0.006 into 5 divided by 0.09, right? So this is 0.3. When you multiply 5 with 6, this will be like 30. So this will be like 0.03 divided by 0.09. 0.03 divided by 0.09. So your mu comes out to be 1 by 3. Mu comes out to be 1 by 3. Next, you need to calculate the value of other moduluses. So the other modulus include the Young's modulus, second one is the shear modulus, third one is your bulk modulus. Okay. But the data given here is like you have a circular bar, a cylindrical bar, over which you are applying the tensile load of 50 kilonewton. So in this question, the scenario given is like this. You have this cylindrical bar. You have this cylindrical bar, and over this cylindrical bar, you are applying 50 kilonewton load. You are applying 50 kilonewton load. Over the cylindrical bar, you are applying 50 kilonewton load, right? You are applying a load of 50 kilonewton, okay? So I'll just write down. So I have to calculate stress, which is equal to load per unit area. So load is 50 kilonewton. So this is 50 into 1000 in Newton. And for area, so this is pi by 4 into 50 square. Because 50 is the diameter of the bar. And this thing is in mm. This is in mm and this is in Newton. So this is the direct stress value I have. Similarly, I have the strain. Which is delta L by L. And we have already calculated it. It is 0.09 divided by 250. So just check. This is 0.09 longitudinal strain, 0.09 divided by 250. So as per Hooke's law, we know this, stress is equals to Young's modulus into strain. Stress is 50 into 1000 divided by pi by 4 into 50 square, which is equal to E into strain, and strain is 0.09 divided by 250, right? So this, do the calculation and tell me the final answer for this. Just do the calculation and tell me the final answer for this. So this is like 50 and 50 will going to cancel out. So you have 1000 by 50 or 4000 by 50 divided by pi. Okay. Then you have 250 divided by 0.09. So this comes out to be 70735. So E comes out to be 70735.53 megapascal. Or you can write 70.73 into 10 raised power 3 megapascal. So this is the value of Young's modulus that you got. So this is the Young's modulus that we have got, right? Once we have the Young's modulus and we have the Poisson's ratio, we can calculate the value of bulk modulus and the shear modulus. So for bulk modulus, E is equals to 3K into 1 minus 2 mu, right? E is 70.73. This is 70.73 into 10 raised power 3. This is in megapascal, which is equal to 3K into 1 minus 2 into 1 by 3, because value of mu is 1 by 3. If this is in megapascal if this E is in megapascal, obviously your K will also be in megapascal because Poisson's ratio does not have any unit. Just do the calculation and tell me the value for this also. So this is 1 minus 1 by 3, 1 minus 2 by 3 will be 1 by 3, and 1 by 3 and 3 will going to cancel out. So directly we have the value of K. So K is equals to 70.73 into 10 raised to power 3 megapascal. So the value of K is also same. Value of K is also same. The next calculation goes to the shear modulus. The next is your shear modulus. For calculating shear modulus, we know that E is equals to 2G into 1 plus mu, right? E is 70.73 into 10 raised to power 3, and this is in megapascal. Then you write 2G into 1 plus mu, and mu is 1 by 3. Again, this mu is unitless, so the unit of G will also be in megapascal. So this G will also be in megapascal, right? Just do the calculation. So this is 4 by 3. 4 by 3 into 2 is 8 by 3. So G is equals to 70.73 into 10 raised to power 3 into 3 by 8 to 3 by 8. So 70.73 into 3 divided by 8. So 26.52. Value of G comes out to be 26.52 into 10 raised to power 3 megapascal. So this is how you need to apply all these formulas which are there for calculating the elastic constants, right? So again, there are 4 relations between elastic constants. And what are elastic constants? First one is the Young's modulus, second one is the shear modulus, third one is the bulk modulus, and fourth one is the Poisson's ratio. So I hope through this numerical you understood how to apply these formulas and what are the relation among these elastic constants. So that is all for today. I hope you have learned many new things in today's session, right? In the next session, we will continue with other forms of stresses. Thank you so much for watching patiently. Have a very good day. Thank you.